Okay, this is OCR, A-Level Physics 2021, Paper 2, Exploring Physics. And I can't show the paper on the screen because unlike AQA, OCR are cool dudes. Here we go, number 1. We have multiple choice first, Faraday's law of electromagnetic induction. And we have two terms missing. The Watt induced is directly proportional to the rate of change of magnetic flux. We know that Faraday's law is this, equal to, or, whatever, and delta phi over T, so it is flux linkage because that is flux linkage there, so it can't be flux density. And the Watt induced in the circuit, it is the EMF, so therefore the answer is D. 2. Monochromatic light. What can be used to explain these bright dots? Diffraction and interference, yes. Not reflection, not refraction, yeah, not those, so the answer has to be A. Easy peasy so far. 2, we have a current of 2 milliamps. We have a PD. We're looking for the energy transferred in 3 hours. So we know that P is equal to VI or IV. So therefore, times it by time, we get energy. So VIT. So it's going to be 6 times 2 times 10 to the minus 3 times 3 hours times 3,600. So I'll tell you what, I can cancel some powers of 10 here, methinks. So that ends up being 12 times 3, so 36 times 3.6. And so I think the answer looks like it's going to be 130. 4, we have two charged spheres. Magnitude of the charges is the same. Okay, what's true? A negatively charged particle will move to the right. No, because we know opposites attract. The direction of the electric field at point P is to the left. No, because electric field lines show the force on a positive charge, so it would be to the right. C, the electric potential at P is 0. That is correct. Now the field strength is not going to be 0. It would be if it was positive and positive, but because it's negative and negative, we have a positive potential here, we have a negative potential here, and we know that total potential is just going to be this plus V plus minus V, so it ends up being 0. So it's the only time that you can have a potential of 0 when you have two opposite charges, and the potential is going to be 0 somewhere in between. Let's just check D. The magnitude of the field strength is 0. You might be tempted to think that's the case, but no. The positive is going to repel a positive charge. The negative is going to attract the positive charge, so it definitely is not 0. Again, it would be if it was two like charges. Oh, we have a rectifying circuit here, full wave rectifier. Sick. So two LEDs are lit in this circuit. So of course positives here, negatives here. So current, conventional current that is going around that way. That's the only current we care about in circuits. And so it's going to be, current's going to come around here of course. And so it can go around there as well and back to there. So it's going to be Q and S, isn't it? Obviously can't go through the diodes in the wrong direction. 6, we have capacitor discharging, and we have the equation for what the rate of discharge is. Fine. So we're being asked what is the value of Q in microcoulombs at time that. Okay, fine. So 100 has gone from this 1,000 to leave us with 99, and so then it's going to be, well, it's 10% because exponential is the way it goes. It has to be the same proportion every time, so it's going to be 10% is lost every time, it looks like. Oh yeah, it's every 0.5 seconds, right? So therefore every 0.5 seconds is going to be not minus 0.2 but 0.1 Q. So basically 10% is lost every time. There we go. So we're left with 810. 10% of that is going to be 81. And so, well, it looks like the answer is going to be something like, well, there's only one that fits that, doesn't it? It's going to be C. 7, thermistor. Okay. So the resistance of the resistor is R, and this is 2.5 R, right? So 2.5 times bigger. The PD across the thermistor is 5. Oh, what's the total PD across both components? Okay, fine. So potential divider, greater resistance, greater voltage, greater share of the voltage, and so therefore, because this is 2.5 times less, that means that this is going to be 2 volts here. 5 divided by 2.5 gives us 2 volts. So therefore, altogether, it's going to be 7 volts. Easy. 8, double slit is used in an interference experiment. What's the separation between adjacent bright fringes for source cell? This is a proportionality question. So let's crack out our equation. W equals lambda d over S. What is staying the same? S is staying the same. So therefore we can say that W is proportional to lambda d. So all we have to do then is put in what's happening. So this is going to 0.8 of its original value, and this is going to 0.5 of its original value. So therefore it's going to 0.4 of its original value. So if it was 1.2, now it's going to be 0.4. So therefore it's going to be 0.48. So the answer is A. 9, stationary wave. We have the length of the tube, and we have the speed. What is the frequency of the sound wave? Well, of course, we need to find the wavelength. So how many waves do we have here? We have 1 1/4. So therefore, we can say that 1 1/4 waves, or 1 1/4 lambda, or in other words, 5/4 lambda is equal to 3.5 meters. Therefore, lambda is going to be 3.5 times, well, the reciprocal of that will divide by 5/4, whatever. So therefore it's going to give us, what's that, 2.8 meters. Cool, so we have the wavelength, and then all we need to do is plug it into our V equals F lambda. We're looking for F, so therefore F is equal to V over lambda. So that's 340 over 2.8, and it looks like it's going to be about 120, yeah, 121, so 120 hertz. So the answer is B. 10, we have an EMF of 6 volts and a negligible internal resistance. Current from the battery is 30 milliamps, so this looks like it's going to be a Kirchhoff's law question. So we therefore have to have 20 milliamps going along this bottom branch there then, don't we? So they're identical resistors. What is the power dissipated? Okay, well that's easy because we have 3 volts across both if they're identical. Easy. So P is equal to IV. So it's just going to be 3 for just one of these for Z times 20 times 10 to the minus 3. They're all in milliwatts, so actually we can just forget about that. So it's just going to be 3 times 60, and that gives us 60 milliwatts. Happy days. Really easy multiple choice so far. 11, we have 2 waves. The waves meet at a point in space. They interfere, and they go superpositioning, superpose, whatever. What is the frequency F and amplitude A of the resultant wave? Well, we know that frequency isn't changed when you have 2 identical waves. It doesn't double or anything like that. So we can see that the time period is 5 milliseconds, so therefore it can't be 100 hertz. It has to be 200 hertz. The amplitude, well, let's have a look. We can see that we have 3 plus 1 there, and so that's going to give us -2 essentially. Let's write it down there. And then, yeah, 3 and -1, so that's going to be 2. So therefore the amplitude is just going to be 2. So the answer is C. 12, flat coil has 200 turns and a cross-sectional area of that. And we have an angle as well, right? Okay. And the angle is between, so we know we're going to be using cos. If you don't know where I'm getting that from, have a look at my easy vectors trick video. It's worth it. What is the flux linkage for this coil? Well, we know that N phi is equal to BAN. And we have B there, of course. But because it's at an angle of 30 degrees, we're not getting all of that B, as it were. We're only getting cos 30 of that. So we're going to put cos theta in there. So that's equal to 0.05 times, or 1.2 times 10 to the minus 4 times by, what was it, 200 times by cos 30. So can I do this in my head? No, I don't think there's any point because I can't do cos 30 in my head. So yeah, there we go. I'm just going to go for it. Timesing these all together, and we end up with 1.04 times 10 to the minus 3. So yeah, the answer is D, because it's that many wubs. Technically it should be wub turns. Naughty OCR. 13, bit of nuclear. We have an isotope. It emits 2 alpha particles and 2 beta minus particles. What is the nucleon number A and the proton number Z for the nucleus of this radium isotope that is produced? So let's just go the long way around, shall we? So let's do 1 alpha. So 4 off the top, 2 off the bottom, another alpha, and then a beta minus. Hang on a minute. We know the proton number goes up, so actually we're going to end up with the proton number, atomic number, of 88. Oh, there's 2 of those, okay. So it's either A or D, and well, we know that the nucleon number stays the same, so therefore it has to be A. 14, ultrasound. We have density, we have speed of ultrasound as well. So our equation is impedance is rho C. So all we have to do essentially is just put in the numbers, so 1.2 times by 1.5. That gives us what? 0.6, so 1.8. And then of course we're going to have to use our bestial equation with intensity. So therefore we're going to say transmitted intensity over original intensity is equal to Z2 minus Z1 over Z2 plus Z1, all squared. So that's just going to be, well, 0.8 over 2.8 squared. So just IT over I0 gives us this, well, 0.082 times that by 100, and we end up with 8.2%. So there we go. That's our percentage. So the answer is B. Finally, 15, radiation detector, and the count rate is measured and recorded every 10 minutes. What term can we use to describe the data shown? Is it exponential? No. Is it linear? No. Is it random? Yes, it most certainly is. So the answer is C. What a weird question to end up on. Good grief. Okay, normal question. 16, normal frequency range of hearing is 20 Hz to 20 kilohertz. Speed of sound is that. Calculate the shortest wavelength a young person can hear. So shortest wavelength is going to be the highest frequency. So therefore V equals F lambda. We're looking for lambda, therefore lambda is equal to C over F, whatever. So 340 divided by 20,000 Hertz, so 2 times 10 to the 4. And we have a sound that is 0.017 meters wavelength. Describe how you can use an oscilloscope, could have done that in my head actually, and any other additional laboratory equipment to determine the actual upper limit of the frequency range of a young person. What? Oh, for goodness sake, how weird is this? You get a speaker and a signal generator, just going to call that a SIG-gen. Increase, what the heck is this? Increase frequency until young person can no longer hear. That's it. That's so weird. Oh, okay, fine. Obtain T time period from oscilloscope. F is equal to 1 over T. Fine. Weird. State one difference and one similarity between oscillations of a stationary sound wave and a progressive sound wave difference. Well, we know that individual points on wave have different amplitudes for stationary wave, whereas for progressive, all points reach the same amplitude. What can we say about similarity? I guess they're both longitudinal, or something like both involve disturbance of, I don't know, displacement of air particles. Moving on. Describe how you can measure the refractive index end of the block by using critical angle method. Draw on the diagram, label it 2. Okay, so we need to make sure that the point is right in the middle. That is not right in the middle. That's a bit better. And what we do is have a protractor here, like so. What we want to do is increase, and there's our normal as well. We want to increase the angle of incidence. Whoops, what we want to do is increase the angle of incidence, that's our I, until the light ray is no longer visible and we have angle of refraction of 90 degrees. So increase angle of incidence until light no longer refracts. We can say R equals 90 degrees, I equals critical angle. And then of course we can say that, well, N1 sine theta 1 is equal to N2 sine theta 2. Let's start off with the whole of Snell's law. Of course, N1 is our glass, N2 is our air, so therefore, and of course N2 is 90 as well, therefore N1 sine theta 1, or sine theta c, is equal to 1, therefore N is just dropping the 1 is equal to sine 1 over sine theta c. Define work function of a metal, the minimum energy required to liberate an electron from the surface of a metal. Work function is 2.3 electron volts. Potassium emits electrons from the surface when blue light is incident on it. Extremely intense light, red light, produces no electrons. Explain these observations in terms of photons and energy. So first thing we're going to say is intensity only affects number of photons incident on metal. Only frequency affects energy of photons. Let's state the equation as E equals HF. If F is greater than threshold frequency, then the energy of the photon is greater than the work function. Therefore, electrons have some kinetic energy to escape surface. Frequency of blue light greater than the threshold frequency. Red light frequency is obviously less than the threshold frequency. Let's state the thing that they like to say, one-to-one interactions as well. There we go. Light from a laser is incident on some potassium. Electrons are emitted. The wavelength is that many nanometers. Calculate the shortest de Broglie wavelength of the emitted electrons. Oh, interesting. Okay, here we go. Okay, so let's find out the kinetic energy of the electrons first. So we know EK max is equal to HF minus phi. Of course, we're dealing with wavelength, aren't we? So it's going to be HC over lambda minus phi. So that's 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by, so that 320 nanometers, so 3.2 times 10 to the minus 7. Tidy us some powers of 10, so minus 7 ends up being 15, and then add 15 onto minus 34, so it gets minus 19. Take away the work function, what was it? It is 2.3 electron volts, so 2.3, but we have to times that by, of course, 1.6 times 10 to the minus 19 to give us joules. So that gives us 6.2, do that 6.22 times 10 to the minus 19 minus 3.68 times 10 to the minus 19. So ultimately that is 2.54 times 10 to the minus 19 joules. Cool. But then we're being asked to find out the, not the energy, but the de Broglie wavelength. So we know de Broglie wavelength is equal to h over p, so over momentum. People often forget how to reconcile them. We have energy, don't we, not momentum. So how do we deal with de Broglie wavelength if we have energy? Well, it all comes down to the fact that energy, kinetic energy that is equal to half mv squared. Multiply both sides and we end up with me equals half m squared v squared, which is basically momentum squared. And so therefore, rearranging this, we can see momentum is equal to square root of 2me. Okay, so therefore we can say that wavelength is equal to h, so 6.63 times 10 to the minus 34 over square root of 2 times mass of electron, 9.1, times 10 to the minus 31, times by the energy that we calculated. There we go. A bit of a beastie question, this. Square root of, I'm just going to do the bottom bit first. So, and then do h divided by that, and I end up with 9.75. Let's go to 2 sig fig, so 9.8 times 10 to the minus 10 meters. Phew. So we have two wavelengths there for starters. Don't get confused between the wavelength of your photon and de Broglie wavelength, and then it's just a matter of figuring out how does energy match up with momentum when it comes to using the Broglie equation. 18, we have a circuit, we have an EMF, we have an internal resistance of that. The other battery, oh great, so we have another EMF and another internal resistance. Marvellous. If I call this setup 2, this setup 1, call this epsilon 1, R1, epsilon 2, R2. And we have the resistance of R. Switch S is closed. On the diagram, draw an arrow to show the direction of the conventional current. Well, of course, it's going to be going anti-clockwise, isn't it? Because the 4.5 volt battery is beastier than the 2.5 one. Easy. Calculate the current I shown by the ammeter. Right, here we go. Gosh. Whew. Okay, so we know that the, oh, actually, this is easier than I think, actually. Easier than it looks, maybe. So we know that we have a total EMF of 4.5, take away 2.4. So EMF we can say is this. So that gives us 2.1 volts. Cool. And then I think it's, yeah, I'm pretty sure we can just use our EMF equation. So EMF is equal to V, but it's going to be IR, isn't it? IR plus IR. Of course, we can factorize this as IR plus R. So therefore, I is equal to epsilon over just the total resistance, effectively. It is just V equals IR. After all, this equation is just basically just, you know, resistors in series, isn't it? So I'm just going to say R total. Why not? So that is 2.1 divided by, what have we got? 0.5, 0.8, plus another 1.2. So that gives us 2.5. So 2 over 2.5, 2.1 over 2.5, sorry. And it gives us 0.84 amps. Insulated wire has a diameter of that. Going to have to find the area of that guaranteed. The number density of the charge carriers is that. It's N. And that's our N there, number of density charge carriers. Calculate the mean drift velocity V of the charge carriers in R. So our equation is this. We're looking for V, so therefore V is going to be the current over all of this other stuff. So that's equal to I over, well, again, that's 4 pi r squared, I guess. Yeah, let's just say it's going to be pi r squared or pi d squared over 4. Let's just say pi r squared. And E, so that is equal to current of, what do we say it was? 0.84 divided by, here we go, pi times, well, it's half of the diameter, so 2.3 times 10 to the minus 4 squared times 4.2 times 10 to the 28 times by 1.6 times 10 to the minus 19. Just about fitting on there. Can I tidy up powers of 10? No, I can't be bothered, to be honest. Okay, I'm going to do the bottom bit again first, just so I'm not making any mistakes. And that gives me 7.52 times 10 to the minus 4 meters per second, 2 sig figs. Yeah, 2 sig figs. Let's go to 7.5 times 10 to the minus 4 meters per second. Current measured by the ammeter is smaller than that calculated in 2. This is because the temperature of R increased due to heating by the current, but it really shouldn't be, because resistors are specifically designed such that the resistance stays constant no matter how hot they get within reason. Without any changes to the circuit itself, state and explain what practically can be done to make the measured current the same as the calculated current. We need to lower the temperature. What a weird question. Use fan, or we can say only switch on when taking readings, and that is good advice, because when you're doing any sort of experiment, yeah, you really want the circuit to be on when you're taking readings. I mean, you're going to be wasting battery anyway, aren't you? Next, B, we have a student doing an experiment. Carrying out an experiment? That seems like bad English. Whatever. So here we have just our standard core. We have a graph, easy. Are we being asked to calculate? Wait, what? There is an incomplete table next to the graph. So E is the y-intercept. R equals minus the gradient. So what we should do really is extrapolate this with a ruler. Going back here. Fine. You should end up with an EMF of about 1.2 volts. Gradient of about 0.8 ohms. I guess if we just use V equals IR for all of these. So V equals IR, so therefore R equals V over I. So just doing that for all of these, and of course P is equal to VI as well. So therefore we just should be filling in these numbers, just calculating these. To what end? I don't really know, but there we go. Oh, I should put zeros in there, shouldn't I? You should too, because we need to make sure that when it comes to any table, we should have a consistent degree of accuracy. So same number of decimal points going down our columns, not necessarily from one to the next. But if we're calculating from 2 sig figs, which we basically are, then we should be going to roughly 2 sig figs. Yes, this one here is 3 sig figs, but it doesn't really matter too much. Okay, so what are we being asked? You calculate R and P to complete the table. Fine. Describe how P depends on R. So we can see that we have max P when the resistance is equal to the internal resistance of the battery. That's it. Moving on. 19, we have a long current carrying wire. Fine. Oh, okay. We know that we're going to have... No, it's going down, isn't it? Yeah, that means that it's going downwards. Wrong way round. If you get your right hand and you point it downwards, that means your fingers are curling around like this. So it's going clockwise. I don't think we really need... Oh, there we go. Draw at least 3 field lines to indicate the magnetic field pattern around this wire. There we go. They might look like equipotentials, but they're not. They are field lines. Arrangement shown. We have this. Okay. Uncertainties, no. Length of the wire. We have the balance reading with no current, and then we have the balance reading with that. So therefore, we can say that the force is equal to mg, or the simulated force anyway, isn't it? Or the simulated mass, rather, I should say. That's going to be 2.2 grams, so 2.2 times 10 to the minus 3 times 9.8. Yeah, I mean, it's still 2.2, isn't it? Times 10 to the minus 2, or in other words, 0.022 newtons. Fine, and I have the current in the wire as well. That's my L over there, isn't it? Cool. What are we being asked to find? Guaranteed B. Yep, calculate the flux density B, including the absolute uncertainty. So let's ignore the absolute uncertainty in the balance readings. Is there an absolute uncertainty in the balance readings? Don't think there is. Well, we can assume there is, whatever. So we're going to say that F equals Bill, so therefore B is equal to F over IL. So that is 0.022 divided by 5 times 6 centimeters, so 0.06. So in other words, 0.022 divided by 0.3, and we end up with 0.073. They say 72, but that's just rounding error, and that is Tesla, isn't it? Okay, the absolute uncertainty then, well, we need to find out the percentage uncertainty in all of these, first of all. So we're going to say that the percentage uncertainty in the length is going to be 0.2 divided by 6 times 100. So in other words, 20 divided by 6 in percentage terms, and that gives us 3.3%. And then what about in the current? Well, that's going to be 0.1 divided by 5 times 100. So in other words, 10 divided by 5. So that is 2%. 2% in our current, we have 3.3% in our length. So therefore, adding these together, the percentage uncertainty in B is going to be equal to 5.3%. So therefore, times this by 0.053, and that gives us 0.004 if we could just go into the same degree of accuracy. So that's going to be our absolute uncertainty. 20, we have a capacitor. We have the EMF is 1.48, so I'm going to say that's our V0. And negligible incident resistance, fine. We have the resistor is that, and we have the capacitance is that. Okay, calculate the time, T, when the potential difference across the capacitor is 1 volt. Okay, so this is charging, and actually I nearly made the mistake of just not reading the question properly. RTFQ, read the full question. I thought it was discharging. So we know that if it's charging, then we can go with the equation V over V0 equals 1 minus this ratio of E to the minus T over R. C. There we go. So therefore, could go with this, or you could use the discharging equation for the resistor instead and just say that there's, well, 0.48 volts across the resistor. Up to you, doesn't matter. Maybe that's slightly easier, I don't know. So all we're going to do is say that, just rearranging this, 1 minus V over V0 is equal to E to the minus T over RC. So therefore, log in both sides, natural log, yes, I can say log, I don't have to say ln, I hate saying ln. It is a log. So that's equal to minus T over RC. So therefore, T is going to be equal to minus RC times by log of 1 minus V over V0. So that's equal to minus 120 kiloohms, so 1.2 times 10 to the 5, times by the capacitance 2000 microfarads, so that's 2 millifarads. So there we go. I think I can do something like that in a second. Log of 1 minus V, which is 1 point, oh, it's just 1 actually, 1 over, there we go, 1.48. This ends up being just, what's that, 2.4 times 10 to the 2, so 240. So popping that in, and that gives me 270 seconds. Like I said, you could alternatively use the discharging equation for the resistor, because it's going to just be doing the opposite. As the capacitor is charging, the resistor is going to be discharging. It's not really discharging, but the PT is going to be dropping for that. So we can use just the V over V0 equals E to the minus T over RC for that, and just use the 0.48 volts for our V. So whichever takes your fancy. Okay, conductive paper. Switches moved from X to Y. Potential difference across the capacitor to half is measured. There we go. So we have K is the resistance of the conductive paper. The resistance of the conductive paper per unit length. Okay, so this is ohms per meter. Fine. Value of C is that. Okay. So we have a straight line. We're going to have to find the gradient of that. Garen flipping T'd. So we have T against L. Okay, so therefore if we rearrange this, we can see T against L is the gradient, and that is equal to CK log of 2. Awesome, we're going to be asked to find K, aren't we? Yeah, we're going to find that. So what did I say? Gradient is equal to T over L, which is equal to CK log 2. Therefore, K is equal to gradient over C log 2. And you should find the gradient to be something like 38 divided by the capacitance was 1.2 times 10 to the minus 3 times by log 2. And we end up with 45,685. So let's do that to 2 figs, so 4.6 times 10 to the 4 ohms per meter. 21. High energy X-ray photon interacts with an electron of an atom through the Compton effect. Describe this effect. Electron is ejected from atom, and then the photon is scattered with increased wavelength. We can say lower energy. There we go. X-rays on soft tissue. There's a cyst. Gross. Attenuation coefficient is that. So that's our mu. We have the intensity is I, 0. There's a small cyst, 2.1 centimeters. So there we go, that's D. The cross-sectional area of the cyst is that. The beam is switched on for 30 seconds. Calculate the X-ray energy incident on the cyst in a period of 30 seconds. Okay, first things first, we're going to have to get our intensity equation for attenuation. That is I over I0, or, you know, I equals I0 or whatever. E to the minus mu x. I mean, we are looking for this, so there we go. I'm going to pop that in there. So that's equal to our first, our incident radiation, so 4.6 times 10 to the 3, 4,600, times e to the minus 0.85, and then that's times by 2.1. They're both in centimeters, centimeters to the minus 1, so we don't need to convert anything there. So I'm going to do the E bit first, and times that by 4,600. And that gives us an intensity on the cyst of 772 watts per meter. But we're looking for the actual energy, and well, that's per meter squared, 772 watts per meter squared. But we're looking for the actual energy. So, well, first of all, we need to find the power, don't we? So if we times that by the area, then that gets rid of the meters squared, or per meter squared. So that's times by 3.4 times 10 to the minus 4. And then if we want to turn that into energy, we just times by the time, don't we? So just times that by 30. Easy peasy. So 772 times 30 times 3.4 times 10 to the minus 4. And that gives us 7.9 joules. See, the attenuation coefficients of the cyst and the soft tissues were similar. This prevented imaging of the cyst using two-dimensional X-ray imaging. Name a different X-ray technique that could be used. We could, of course, use a CT scan or a CAT scan, and give a reason for this as well. It gives a 3D image and better contrast. So there's two reasons that you can choose from. So you won't get a mark for saying more detail. It's all about the contrast. 22. The medical trace of fluorine-18 is used in a PET scanner. It's a beta plus emitter with a short half-life. Describe how the fluorine-18 nuclei are located in a patient using a PET scanner. So the positrons annihilate with electrons they encounter in patient. 2 gamma photons produced, traveling in opposite directions. Then we can say difference in arrival times, used to calculate point of origin. There we go. 23. Explain the function of the control rods and the moderator in a nuclear fission reactor. Let's go for the moderator first. Moderator reduces energy of neutrons to thermal speeds, so they have thermal speeds, whatever, such that they can be absorbed by uranium nuclei to cause fission. Control rods absorb neutrons without causing fission, as to reduce the rate of fission in reactor. Cool. B, some nuclear fission reactors use uranium-235 in the future using hydrogen-2 in fusion reactors. Yeah, they've been saying this for 50 years. I'll believe it when I see it. There we go. Describe the similarities and differences between fission and fusion reactions. Explain with help of calculations which field produces more energy per kilogram. Okay, so similarities maybe. Similarities. Products are lighter, therefore mass has been turned into energy in both cases. And we could also say total binding energy increased. Or we might say average binding energy per nucleon as well. Differences. Fission, of course, we have neutrons that can cause further fission or induce further fission, we might say, whereas energy from fusion must be sufficient to cause two hydrogen-2 nuclei to become so close, or to, let's say, overcome electrostatic repulsion to cause further fusion. That's why it doesn't really work too well. It's not very discrete. We call that a chain reaction. Okay, so we're done with the wordy stuff. Let's do some calculations. Maybe I should have done that first because I'm going to have to keep going back up and down. Yay, well done me. Okay, so, okay, it's not too bad. So we just have some approximate energy produced per reaction. So 200 mega electron volts and molar mass of fuel material. Okay, so it's 200 and mega electron volts, 0.235 kilograms per mole, 4 mega electron volts, 0.02. Okay, so in a mole we have the same number of nuclei, but of course we do need twice the number of nuclei for fusion than we do for fission, because we only need one for fission to happen. We need two for fusion to happen, don't we? So what we can say is that, let's just think about it in terms of proportionality. Energy per kilogram is going to be proportional to energy from one interaction, as it were, but also times by number of, we might say particle density or whatever. We can say number of nuclei in a kilogram. So actually we can say that, therefore, so we can flip that on its head, we can say it's inversely proportional to kilograms per mole. Basically, how light are they? The lighter the mass, the more particles you'll have in a kilogram. So there we go. So we can say that for fission, we can say this is proportional to, so energy per kilogram is proportional to 200 divided by 0.235. That gives us 851. No unit, this is just all relative. So we've done that. What about fusion? So energy per kilogram is proportional to 4. But it's not going to be 4, is it? That's the thing. So, well, I tell you what, we'll say 4, but then 0.002 kilograms per mole. Actually, no, I'll tell you what, I will call it 2. So I'm going to call that 2 because we know it's going to be ultimately half of the energy made by each particle, because there's 2 required. So divided by 0.002, and that gives us the 1,000. So therefore, even though it's half, fusion produces more energy per kilogram. But they're still roughly the same, aren't they? 24, we have basically electrons being deflected. We have the PD, we have the distance, so this is electric fields, isn't it? We have the U, and we have X. So the vertical acceleration A between the plates is that. So it's just going to be F is equal to EQ. And of course, parallel plates, E is equal to V over D, so V over D times Q. And of course, F is equal to MA, so therefore that's also true. So therefore acceleration is equal to VQ over MD. So that is 4,000 times charge of an electron divided by the mass, which is 9.1 times 10 to the minus 31, times by the distance, which is 0.08. So let's pop all of that in. And sure enough, we end up with 8.79 times 10 to the 15 meters per second squared, 8.8. Length of each plate is that, so this is basically just now projectile motion. So the time taken to travel this length is that. So we know the speed is 6 times 10 to the 7 meters per second. So just speed equals distance over time, because there's no acceleration going on horizontally. Therefore, time swapping these two around is equal to d over v. So that is 0.12 divided by, what do we say? 6 times 10 to the 7, yep. And I'm sure that's going to give us, yep, sure enough it is, isn't it? Divided by that is going to be 2 times 10 to the minus 9 seconds. Next, calculate the vertical deflection x of the electron. So this is just SUVAT, so we want to know how far it's going up right there. That's our S or our X. I don't think they want to say, yep, that's right. So we're going to say that SUVAT S is equal to, what we're trying to find out, U is equal to 0 because there's no initial vertical velocity. We don't care about that. We said the acceleration was 8.8 times 10 to the 15 meters per second squared, and we have a time of 2 times 10 to the minus 9 seconds. Okay, so we're going to be using S equals ut plus half ag squared. Classically, u is 0, so therefore we forget about that. So this is therefore equal to half times 8.8 times 10 to the 15 times by t squared, so that's times by 2 times 10 to the minus 9, or in other words, if that's squared, then I'm just going to call that 4 times 10 to the minus 18. So therefore, that's equal to 4.4 times 10 to the 15 times by 4 times 10 to the minus 18. I don't think I need a calculator for this. So therefore, this ends up being then minus 3. And 4.4 times 4, that gives us 16, so 17.6 times 10 to the minus 3, or in other words, 0.0176. We've been asked for it in meters anyway, didn't even need a calculator. There we go. Probably should go to 2 sig figs though. B, the arrangement now is used to investigate positrons emitted. The speed is the same. The initial path is the same. Sketch the path of the positrons. Well, it's just going to be in completely the opposite direction, like so. Easy. And what have we been asked? Beta minus particles emitted from a radioactive source have a range of speed. Describe and explain how a uniform magnetic field can be applied in the space between the charged plates to select beta minus particles with a specific speed. No calculations are required. Cool. So therefore we can ensure that magnetic field strength or magnetic flux density is such that the force due to it equals force due to electric field. So of course we know that FB is equal to BQV. We know that electric field is equal to EQ. So therefore, if BQV is equal to EQ, then therefore they cancel, and therefore velocity is equal to electric field strength over magnetic flux density. When achieved, only particles with correct speed or selected speed will have balanced forces and therefore will not be deflected. Of course, the magnetic field needs to be at 90 degrees perpendicular to plane here. So in or out of the page, of course. So something like that going in. And therefore we can block path at end of plates to stop deflected particles from leaving the end. There we go. Oh, there's one more question. Flip me. 25 researcher is doing experiments on radioactive solution in a thin glass tube. Okay, we have a half-life, 10 minutes, 10 hours. Particles emitted, alpha, beta minus. Right. Solution has the same number of nuclei of X and Y at the start, so they have the same N0. State and explain which material has the greatest activity at the start. Well, of course, if it has a shorter half-life, then that means that therefore there must be more decay happening, a greater rate of decay. So X, as its half-life is shorter, therefore greater rate of decay. Why is it dangerous for the researcher to handle a test tube with bare hands? Easy. Nuclear radiation emitted particles can be absorbed by skin and cause damage to tissue. Is it the same for both? Will alpha particles go through? Probably not. So we're going to say there's beta minus only. as alpha will not penetrate glass. There we go. You might not have caught that. You might be tempted to think the alpha particles go through because light does this, doesn't it? Carbon-14 is produced in the upper atmosphere, blah, 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 blah. State the proton number of particle X. Okay, so therefore it has to be 1 in order for it to balance out. And then this has to be 15, doesn't it? And that has to be 1, doesn't it? So therefore it's just 1. Weird question. Oh, binding energy. Yes, I love binding energy questions because they're really, really easy. Use the data to calculate the binding energy per nucleon of the carbon-14 nucleus. Okay, so we have our masses. So therefore we are going to say, okay, so the difference in mass between the constituents and the actual nucleus as a whole is going to be equal to, well, we know that particles by themselves are heavier, so we're going to say 6 protons, so 6 times 1.673 times 10 to the minus 27. Everything's times 10 to the minus 27, so we're going to leave it as that for now, plus 8 times mass of a neutron, again, times 10 to the minus 27, minus the actual mass of the nucleus. Oh, they've given us it in U. Oh, that's okay, fine. So we're just going to say take away 14 times by 1.66 times 10 to the minus 27. I feel like that should be 3 sig figs, but whatever. So of course this is the constituency, and this is the nucleus together. And I end up with 0.198 times 10 to the minus 27. Then I have to turn that into energy, and so we're going to MC square that bad boy. So times that by 3 times 10 to the 8 squared. In other words, times by 9 times 10 to the 16. And that gives us 1.78 times 10 to the minus 11 joules. But we want it per nucleon, and so therefore we have to divide that by 14 once more, and we end up with, so I'm going to go to 3 sig figs, 1.27 times 10 to the minus 12 joules per nucleon. Hope you found that helpful. If you did, please leave a like. If you really found it helpful, consider hitting that super thanks button, put a tip in the jar. It really helps me keep going making these past paper videos. If you want to see the rest of the OCR papers, then click on the card and it'll take you to the playlist. And I'll see you next time.